Okay, this video is gonna do what we wanted to do from a long time ago. Learning more about LLVM, understanding LLVM, and also this relates highly to the MLIR series that we did. So after this, we are going to either go back to MLIR or move to a few other topics in LLVM or compilers, and then probably go back to MLIR. We'll see how that goes. Alrighty, so let's get into it. So this is from Strumenta. It's written by Mauricio Taverna. Mauricio sounds Italian. No, it doesn't sound Italian. Maybe it is. I don't know. Okay. Mauricio Taverna. Maybe it is. I don't know. He's a software engineer with 15 years of experience in software development for the banking and financial industry. He works close to the customers to ensure that design, architecture, and implementation have a real positive impact on the client's project. Alright, so there is that. Okay, so he probably knows what he's talking about. Table contents is what is LLVM, LLVM infrastructure, the RPG language, implement LLVM frontend with Antler and NBSP. So we learned Antler is a parser generator. We have a symbol table. We have the abstract syntax tree, the LLVM IR AIP, generating the LLVM IR data declarations, generating the LLVM IR code generation, runtime functions and NBSP, debugging, conclusions, and more stuff. Okay, so first figure out what is NBSP. Ampersand NBSP is actually one of the most frequently used HTML entities. NBSP stands for non-breaking space, meaning that strings separated with this entity will not be separated and put into separate lines. Oh, actually. Non-breaking space. So enter non-breaking space. That's probably what this is. Anyways, in this article we will explore the implementation of a simple compiler able to translate the IBM RPG programming language into executable machine code for modern hardware. It is not a full-featured RPG compiler. It implements a few basic constructs of the language, but it is good enough to understand how the LLVM infrastructure can be used to handle a high-level language. The topics covered in this tutorial are creating the compiler frontend with Antler, using the LLVM infrastructure and core libraries to generate the machine code, generating the debug information for source level, build level debugging, to generate the machine code, generating and debug information for source level debugging. The main benefit of generating machine executable code is the optimal performance and minimal requirements about the runtime environment. As usual, the source code of the project is available at the GitHub Strumenta article LLVM RPG. The LLVM infrastructure is mainly in C++, therefore this is a C++ project. Alright, what is LLVM? Writing a compiler is software able to translate high-level human-readable code to an executable machine code. Involves a lot of work. However, by using the LLVM, we will obtain two main benefits. The executables we will obtain will be very fast, as LLVM is a mature industrial grade project with great optimizations. LLVM is able to generate machine code for different platforms. By writing our own front-end file language RPG, we will be able to get executables for all platforms supported by LLVM without extra work. One thing to mention, we need to go and find out the arguments against LLVM. I mean, LLVM is like almost everywhere right now, but I don't think, and nothing is perfect. So there's definitely some design sacrifices that these guys made. So this works so general. So we're gonna go through that and see what that is about. Anyways, more in details. LLVM provides an infrastructure that simplifies this process, providing tools and APIs to write a compiler with an existing language or to implement a brand new programming language. It is designed to be very modular and supports all the compilation phases, including front-end processing, code generation, optimization, and so forth. The major building blocks of LLVM can be subdivided in three logical categories: the front-end, the intermediate representation IR, and backend. So you have your C++ and Haskell. These are the front end, and then you go through the intermediate, and then these have to be mapped to x86, which are the Intel chips and the ARM chips, and then these guys have their own machine code. The front-end components are responsible for translating the source code into the intermediate representation IR, which is the heart of the LLVM infrastructure. The IR is used. So intermediate representation is the heart of the LLVM infrastructure. The IR is used through all the LLVM compilation phases and can have a different format based on where it is stored: in the compiler memory, on disk as bitcode, or as a human readable assembly language. The intermediate representation IR is a static single assignment representation that provides type safety, flexibility, and the capability to implement high-level language. The backend module is responsible for translating the IR to a specific hardware such as the Intel x86 or the ARM architecture. Generating the machine code for a specific CPU model is a very complex task and requires a deep understanding about a lot of low-level details of the instruction set. In addition, the machine code optimization is another task which involves complex algorithms hard to develop. The machine code optimization is another task which involves complex algorithms hard to develop. Debug and maintain. The reason why LLVM chose a static single assignment representation is because it makes it possible to apply a bunch of well-known code optimization algorithms. The LLVM backend takes in input a valid IR code and generates the optimized machine code, simplifying the compiler implementation. The LLVM project is released under the Apache license v2 with some exceptions, which allows to include the software as part of commercial products. Alright, LLVM infrastructure. In the installation of the LLVM infrastructure depends on the target operating system. The easy way to download the binary distribution from LLVM.org, as mentioned on the website. There are differences between the platforms. The second option consists of cloning the GitHub repository and building the LLVM infrastructure from scratch following the instructions. LLVM is a C++ project. CMake is required to generate the project files, and C++ compiler to build the project binary tools and libraries. I choose the second option, and I built the LLVM project on a Ubuntu Linux machine. The process took many hours, and I have to fix some minor issues such as missing dependencies. I personally prefer compile the project from scratch when possible to become familiar with the structure of the project and the binaries created. Once LLVM infrastructure is ready Once LLVM infrastructure is ready, it is possible to take a look at human readable intermediate representation using CLang, which is a front end for languages for the C language family. Hello.c is gonna be for the shell invoke the CLang, providing the command line switches to generate LLVM intermediate representation. So we have CLang flag emit LLVM -s hello.c and object hello.ll. The CLang will generate hello.ll as output. So you have your module IDs hello.c, your source file name hello.c, target triple. You have your x86 PC Linux and a private unnamed address constant 4xi8. See this align 1 function attributes no inline, no unwind, opt none UW table. Define DSO local i32 at main. Alright, so i32 is probably what this returns, yes. And now we have a line, you allocate 3 variables and then you store 1 to 1, you store 1 to 2, for 4 you load an i32 of this, so 1, and that you're gonna have 2, and then 6 you add 4 and 5 because you're not touching values of 1 and 2. You store 6 in 3, align 4. Well, it's i30. Well, I don't know why it says i32 and align 4. You understand? Because i32 it's obviously 4 bytes. But why is it aligning it to? Oh, maybe it's because of the. No, it's not because it's struct. Not sure, but we'll figure it out. And then you have the add printf inbounds. That, and then it's printing get, and then returns nothing. So i64 Alright, I feel like that's good enough time that we spend on it. The file hello.ll is the hello.cc program translated into the LLVM IR. It is possible to execute the IR running the LLI, which directly executes the IR. So you can say LLI hello.c hello.ll, and then you will get this. What did LLVM stand for? What does LLVM stand for? Ah, come on. Low-level virtual machine, okay. To create an executable binary, we can pass the IR file to CLang as CLang-x intermediate representation hello.ll that output hello.out, and then you run the out. The example above, the executable target is the host machine CPU. However, LLVM can generate this assembler for many CPU models and can also generate bitcode for the WebAssembly runtime. And the RPG language. So, RPG language was the RPG language report program generator was developed by IBM in 1959 with the purpose of generating reports from data files. At Strumenta, we know quite well the RPG program as we created an open source JVM interpreter for it, available on GitHub. More on this later. The language has evolved over time, and nowadays software in RPG is still used and maintained in many industries and fully supported by IBM. Although the most recent version of the language provides a free format source code entry, the examples provided are in the original fixed format definition specification, which requires a specific positioning of the code within a row. Okay. The example declares the NBR variable, which is a scalar variable with 8 digits and 0 decimal. Statements are identified by C below an example of an assignment. Alright. Okay, so we are writing programming RPG right now. Alright, implement an LLVM frontend with Antler. The frontend parser in this project has been generated using Antler. Starting from the open source programming of the RPG language created by Ryan Eberle and available on GitHub as part of Jericho project. Jericho is an open source JVM interpreter designed at Strumenta and developed in collaboration with sme.uop, a client of ours. Antler generates the lexer and parser that are used to feed the symbol tree table to create abstract syntax tree. Then the code generator traverses the AST to generate the LLVM IR. The compiler is written in C and C++. You can find the detailed information about generating parsers for Antler in C++ in Getting Started with Antler in C++. The compiler architecture is pretty straightforward. The lexer and parser are generated by Antler starting from the grammar files. The parser implementation translates the parse tree in the abstract syntax tree and populates the symbol table. The code generator processes the AST and the symbol table, producing the IR as output. Okay, so we have RPG, RPG frontend, RPG lexer, RPG parser. Antler provides these by giving it somehow the grammar of the RPG. And you're gonna get from the parser a symbol table and the abstract syntax tree, and then you move to code generator. For code generator, you will use the LLVM libraries, and then you will have the intermediate representation generated by LLVM. Okay, to implement translation from the parse tree to the symbol table and the AST, it is required to extend the visitor class generated by Antler. Depending on the complexity of the language, the visitor subclass can become huge. To keep it simple, the process has been divided in two phases. The first process, the data declaration, which populates the symbol table, and the second takes care of the statements and the AST generation. This design decision allows to maintain two separated visitor subclasses with a well-defined behavior. Alright, so provides functionality to parse expression used by both subclasses, process the statements, creates the abstract syntax tree, So we go from Antler. You have your RPG parser base visitor. Then you go RPG visitor provides functionality to parse expression used by both subclasses. Then okay, so you start from RPG declaration visitors because I'm not sure if it can be shown in the video, but the flashes go up and then these flashes go down. And then process the data declaration and store the symbols in the symbol table. And then on this side, we have process the statements and creates the abstract syntax tree. And this is where your RPG code visitor is. The RPG visitor extends the Antler generator parser and implements the common functionality used in the subclasses, such as the expression evaluation. The RPG declaration visitor is responsible for processing the data declarations and populating the symbol table, while the code visitor creates the AST. The RPG declaration visitor is responsible for processing the data declarations and populating the symbol table, while the code visitor creates the AST. Alright. RPG declaration visitor file this declaration visitor dot visit 3 symbol table, it dumps it there. And then we have second pass parses. Ooh, we know about passes. And then so first pass is RPG declaration visitor. Why is this beer so warm? Anyways, so first pass parse declaration RPG declaration visitor file this, and then declaration visitor the visit tree symbol table calls dump, and then you have your second pass. You go RPG code visitor. So first declaration and then code visitor. You get the file. This, I don't know what this is. And then you visit the tree. Where is the tree coming from? And then code generation. Code generator LLVM asterisk generator. A new generator LLVM file. Emit debug info. Generator calls process symbol table. And you pass it to your AST. And then you have your generator dump. So you get a new generator and then you pass it to it your symbol table and your AST, and then it gives you all the things you need from LLVM. So you have two passes, one making your symbol table, one making your abstract syntax tree. Not exactly, but this is what it looks like. I don't know where this and this comes from, but yes. The last section performs the code generation. It takes the symbol table and then the AST and produces the LLVM IR. The emit debug info is used to instruct the code generator to include the debug information that can be used to run the code with a debugger. Symbol table. The symbol table is a database that contains information about variables, subroutines, data structures, and so forth. The design used in this project allows to store RPG data declarations. So symbol table scope map is a symbol, and then you get your add and your gets. You give it a symbol, you get the scope, and then you have your symbol, which has a name and then has a type, and the type is a list. It's a list of symbol type. And then symbol type links to symbol specifier, struct declarator, array declarator, and function declarator. And then you have to define those. Yes. Yeah, you see it's generic. Why? Because your symbol, you have a symbol for a struct, and that struct could have a bunch of symbols, and that's why you have a list for those symbols. And then you have a struct declarator, that's again a list of symbols. So you have symbols that are designed there. It's like integer, chars, characters. I don't know why they call it char, but character, boolean, maybe all the different integer, float numbers, all that. And then what you do is basically create other symbols and you move on, right? And then you have a function declarator that gets the arguments, maybe a return value. I would think that is the case. No, you don't think so? Maybe this is different, I don't know. A symbol is represented by its name or one or more symbol types, which stores the characteristics of the symbol, such as the size, the number of decimals, or the list of parameters in case of a function. The subclasses of the symbol type classes are used to store this kind of information. The key to access the symbol table is the name of the symbol. Symbols are organized in scopes. In this particular implementation of the RPG language, all symbols are global, therefore all the symbols are stored in the same scope. For example, consider a simple scalar definition in RPG. The declaration defines NBR as a standalone field, which is an ordinary scalar variable. It has a name NBR, a definition of type S, a scalar 8 digits and 0 decimals. This RPG is really a program, so imagine you have 8 digits limited to that, and then you have no decimals, so you would say just that. The representation of, I don't know what they were thinking. What were the IBM engineers thinking that they created this? Instead of having like standard integers and stuff like that. Why did this guy choose it differently? I don't know, but we can figure that out too. Right, yeah, okay. The representation of the declaration in the symbol table would be an instance of a symbol class with a symbol specifier, which contains the relevant information about its type. The symbol is stored in a map using the name as the key. So symbol table, your key has NBR, then the symbol is NBR, and your type is a symbol specifier that has size 8, no decimals. Now let's consider an array declaration. As in the previous case, the representation in the symbol table would be an instance of a symbol class with a symbol specifier and an array declarator. Now let's consider an array declaration, D NBR. I'm not sure what D stands for here, maybe it's decimal, but there's decimals here. And then you have the dimension of 10 giving it an array. So you have in your type collection now an array declarator of 8, and then you have a size 8, and you have your decimals as well. Alright, the symbol table API provides a method to add a symbol to a particular scope. During the declaration processing, the RPG declaration visitor class detects the data declaration, inspects the syntax tree, and creates an instance of the symbol with the appropriate attributes. For example, take a look at the following code snippet, declaration CPP. Any RPG declaration visitor is this is some C++. Okay, so this is the class name, and then you have this visit a declaration specification. Declaration specification context, you have it in a pointer context. You have your shared pointer symbol, this, parse symbol, ctx, compiler symbol type, symbol table. From compiler, get the symbol table, add the symbol to it. You catch RPG exception, don't touch that, and then you write down an exception like this, error, this file, this, get line, so get the line value, and then get the message. So E, that's the exception that LLVM is throwing, I guess. Yes. Return RPG parser base visitor. Visit declaration specification, and then you have your context. The processing of the parse tree is implemented within the parse simple method. So you have your shared pointer symbol, and then you have your RPG declaration visitor parse symbol, a declaration specification context, pointer context. If context is DS name, then give it integer size of 0, integer decimals equals 0. Then you have standard string temp, stx, ds name, get text. That's where the declaration visitor is. And declaration visitor is, it's different than the code visitor. Declaration visitor is where the symbol table is, and then code visitor, that's probably the two passes that we are having. This is the abstract syntax tree. Alright. The processing of the parse tree is implemented within the parse simple method. So we have all of this. If name not empty, then get the s to I. What is s to I? Type to integer. Not sure. String to integer. And then now you have your context decimal position. You call it is number, context decimal position, get text, string to integer, you do that, and then you have your decimals. And then if decimals is greater than 0, you throw an exception. But if it's not, I'm not sure where this came from, but maybe if we go through their GitHub repo, we will understand something from there. Right? I think so. I think so. Sure. And then you have your create the symbol and then specifier, shared pointer symbol, the type symbol is make shared symbol, name, syntax, that, syntax ds name get start get line stx shared pointer symbol specifier equals std make shared symbol specifier s. Okay, so that's your s. That was the type, right? Like DNR was the name, S is the type. And then you give it the size, you give it the decimals like this. And then you go for auto keyword in a syntax context keyword. If keyword dash dimension int array size, you allocated array size, and then you have your std shared pointer declarator equals std make shared array declarator array size symbol add declarator if keyword key integer. What is that? In if keyword ends simple expression std shared pointer expression rpg visitor parse expression keyword ends simple expression specifier that gets set value expression else std shared pointer expression. What is an expression exactly again? An expression. Oh well, the expression was the whole thing, right? The declaration and the whole thing. I mean, let's not go backwards right now. And then this, that. You have your shared pointer expression. You get expression. Your RPG visitor parse expression. Keyword key that symbol that return symbol throw RPG exception invalid identifier throw that unable to parse declaration although the symbol table structure is able to represent typical RPG data declaration. LLVM provides support for fixed point arithmetic and data types. For the scope of this project, only the 64 integer type is supported. Alright, so now we move to abstract syntax tree. The second pass of the compiler consists of the processing of the code statements and expressions and generating the AST. The second pass of the compiler consists of the processing of the code statements and expressions and generating the AST. All the nodes in the AST are subclasses of the node class, which store information about this statement, such as the line in the source code. The type of the accept method invoked by the visitor when traversing the tree. So you have your generator, you have your node, you visit expression, you visit identifier, you visit integer literal, you visit assignment, you visit select, then you go on node, you go back to itself, line integer type token, nodes is a vector of the node, accept a generator in this node, and then you have expressions or you have statements. And then you have identifier or integer literal or assignment or select for RPG. Let's just do a double check. Expression versus statement. Okay, you state it, you express it. Come on. Expressions can be assigned or used as operands, while statements can only be declared. Alright, so a statement is when you declare something. Expression is like when you actually have value. Okay. Assignment and select integer literal identifier. This class diagram is a simplified version of the actual AST, but provides the basic idea behind the data structure. The node class contains a vector of node instances that implemented the tree structure. The RPG code visitor extends the antler generated visitor and implements the logic to create the tree structure. Creating and inserting the nodes into appropriate branch. For example, when the parser detects an assignment statement, it extracts the relevant information from the parse tree, creates the appropriate node subclass, and inserts it to the AST. So in the parser.cpp, you have your antler CPP. Any RPG code visitor. So you're declaring it basically, this function here. Visit CS evaluation. CS evaluation is CS eval context. You get the context. If context.target is true, sharing string, you get the context is target. Then you get the text of the target, and then if that target is a string, then the first statement basically is saying if it exists, get the text of it, and then and then short pointer is your expression. Expression is equal to parse expression, context fixed expression, and then you have short pointer assignment statement. And then assignment statement is target expression, and your context getting started from this and then the line. So context is probably the file you have, and then the lines inside of it. Right, yeah. Add the node to the AST, and then you return RPG parser base visitor CS evaluation, add node context. Alright. The add node method implements the logic to insert the new node into the proper position within the tree. Each node implements the accept method, which takes a generated class as a parameter and invokes the corresponding visit method implementing the visitor pattern functionality. Assignment.h is a class assignment statement is public statement. You public, and then you have your LLVM value. It's a pointer. Return the pointer. Oh my god. Return the pointer. Generator pointer v void pointer parameter equals to null pointer by default. Override it and return the v visit this param. Alright. What is this keyword in C++? The keyword this identifies a special type of pointer. Suppose that you create an object named x of class A, and class A has a non-static member function f. If you call the function x.f, the keyword this in the body of f stores the address of x. So this is actually the address or the pointer to itself. Wow, amazing. Okay, the code generator is the base class. declares a visit method which takes the node as an argument for each subclass of node. The concrete generator LLVM is derived from the generator class and implements the visit method. Each method implements part of the code generation for the specific ASD node. The instructions produced during the code generation are maintained by the generator LLVM class through the LLVM API described later. Okay, so now your generator.h has these. What is virtual keyword in CPP? The virtual keyword can be used when declaring overriding functions in a derived class, but it is unnecessary. Overrides of virtual functions are always virtual. Virtual functions in a base class must be defined unless they are declared using the pure specifier. All right. You have a bunch of visits. You're overloading these, and then what is this? Maybe that's the default value for this pointer, right? It's the only way it makes sense. Assignment statement, math expression, comparison expression, integer literal, identifier, select statement, for statement, subroutine declaration, subroutine invocation. These are all in the generator. Ew, interesting. Math expression. Select statement, for statement, subroutine declarations. So there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 A's using here. Okay, now. All right, you know what? I'm tired right now, so I'm gonna break this article into two parts. We learned about how the antler works. He basically made his symbol table, and then his abstract syntax tree. Now he's gonna use those and call the LLVM IR API to basically use LLVM for the backend part of this RPG language. So we're gonna go for maybe a chip or a non-technical video for the next video. But yeah, I have to take a break from compiler. So that's it for this video. I'm gonna see you in the next video in the second part of this article. Thanks for watching.